Hello, welcome to Electrical Circuits, part number 18. We'll discuss resistive inductive or RLC series circuit analysis. As you see in the schematic, we do have the series circuit. We leave the power source with one path coming through the resistor, still one path coming through the inductor, still one path going into the capacitor, and coming back out of the capacitor, we still only have one path. We have 60 hertz for our frequency, 240 volts for our total voltage. We have a resistance of 12 ohms, and an inductive reactance of 24 ohms, and a capacitive reactance of 8 ohms. Now we're going to use the Pythagorean theorem and c squared is equal to a squared plus b squared to find our impedance. But because we have inductors and capacitors both in there, and the way that they operate, they're going to cancel part of each other out, so we have to add a little twist in there. We're going to take their difference. So the way we're going to use the Pythagorean theorem is Z, our impedance, is equal to the square root of R squared plus, open our parenthesis, X sub L minus X sub C, close our parenthesis, and square it. Now, if you can't remember whether X sub L or X sub C goes in first, it really doesn't matter, because of our order of math operations. Please excuse my dear Aunt Sally. Parenthesis, exponents, math and division in the order they come, addition and subtraction in the order they come. Well, since our difference is inside of the parentheses, if we come up with a negative number, it'll be inside of those parentheses, so it'll be a negative times a negative. So it really doesn't matter there which direction you get. The math will take care of it. Now our resistance of 12 ohms will take the square root of that 12 ohms, which will give us 144 plus, close our parenthesis, and we'll take the difference of our X sub L of 24 ohms and our X sub C of 8 ohms, and then we'll square that difference, and we will come out to be with 20 ohms impedance for the total for this circuit. Now that we have our impedance, we can find our current total using the pi wheel of our formula. So, or not the pi wheel, our Ohm's law. So our current total is going to be equal to our voltage total divided by our impedance. So our voltage total of 240 volts divided by that 20 ohms will give us 12 amps. Now, because this is a series circuit, and the current remains constant through all components in that circuit, we can say I sub t is equal to I sub r is equal to I sub L is equal to I sub C is equal to that same 12 amps. So we can go ahead and populate all of those with the 12 amps. Now we're going to be looking for a voltage drop at the resistor. So V sub r is equal to I sub r times R. That's Ohm's law again. So I sub r of 12 amps times our resistance of 12 ohms gives us a 144 volt drop at the resistor. The voltage at our inductor is going to be equal to our current at the inductor times our inductive reactance. So we have a current at our inductor of 12 amps times our inductive reactance of 24 volts, giving us 24 ohms, giving us 288 volts. Now we're going to go for the voltage drop at the capacitor. Is going to be equal to the current of the capacitor times the capacitive reactance. So we have that same 12 amp current, and we have a capacitive reactance of 8 ohms. Multiply that to give us a 96 volt drop across the capacitor. Now we're going to find our apparent power. So our volts ampere is equal to our current total times our voltage total. So we have a total current of 12 amps times a total voltage of 24 volts, giving us 2.88 kilovolts ampere. So 2.88 kVA. Now we're going to use pi of the power formula, and we're going to find out our true power. Again, it's over the purely resistor part of the circuit. So P is equal to I sub R times V sub R. So I sub R is 12 amps V sub R is 144 volts, which will give us 1.728 kilowatts. Again, true power is the only one measured in watts in the AC when we start mixing the inductors and the capacitors and resistors or any combination of those. Now we'll figure our bars, our wattless power at the inductor is going to be equal to I sub L times V sub L. So 12 times 288 giving us 3.456 K bars. And our var sub C will be the current at the capacitor times the voltage at the capacitor. So our 12 amps times 196 volts is going to give us 1.152 K bars there at our capacitor. Now we're going to look for our inductance. We'll use the formula of inductance is equal to our inductive reactance divided by 2 times pi times the frequency of 60 hertz. Our inductive reactance here is 24 ohms. So 24 ohms divided by 2 times pi times 60 will give us 63.66 millihenries. And then our capacitor, we'll use 1 divided by 2 times pi times the frequency of 60 hertz times our capacitive reactance. So C is equal to 1 divided by 2 times pi times 60 times 8, giving us 331.57 microamps. Now we're going to look for our power factor. We have the power factor and our angle theta to go. So our power factor is the ratio of true power to apparent power. So our power factor is equal to our power divided by our apparent power. So it's that ratio. And so we have a power of 1,728 watts. And we have an apparent power of 2,880 volt ampere. And so when we do that division, it'll give us 0.6, or since it's a ratio, our 60% power factor. Now that we have our power factor, we can find our angle theta, which is simply the arc cosine and plug in the power factor. So our angle theta is equal to cosine raised to the -1. Put our power factor inside the parenthesis as the decimal at 0.6, giving us 53.13 ohms of phase angle. Here's all the numbers that we calculated. We have a list of it. Now we're ready to go out there to a live circuit with our meter and make live readings so that we can compare to this. Are we close? Go look somewhere else. Are we way off? Better look at that part of the circuit a little bit closer. There is an issue there. Thank you for joining us in this part 18 of our series in tutorial.